Alright, what I've written up there says relative humidity, temperature, and condensation / deposition. So today's class is all about the water that's in the air,
I think that would just be a fun time.
how temperature affects the relative humidity, and then how that in turn affects condensation and deposition, which are the movement, as you know, of water from the gas state to either a liquid state or a solid state. And if you take nothing else away from today's class, you're only going to take one thing away from today's class. It's going to be the very first thing I wrote on the board.
It's going to be a lava lamp. Because I'm going to take that from you.
Alright, take it.
And here's the very first thing, the most important thing to remember. Warmer air masses can have a greater capacity for water. They can hold more water.
That's dumb.
Okay, thank you for having that.
Not quite.
Mr. Green, so can I really take that lava lamp? Because I don't have one at home.
No, I like to have it. It does a great job of allowing me to it demonstrates convection very well.
What? I do. I should put it place. I don't want it. I really don't want it anymore.
Okay, so what I've written there says warmer air masses can hold more water, and in parentheses I've written larger capacity. If something can hold more water, if this air mass can hold more water, it's got a larger capacity for water. And by the same token, the converse is also true. Cooler air masses cannot hold as much water. They have a smaller capacity. Cooler air masses cannot hold as much water.
Where's he going?
Who?
Jack.
He's an idiot. Did he just walk out?
He's just going.
He's just going.
He's out.
Okay, now I'm going to ask you guys to, number one, direct your attention here. And number two, help me
No.
by telling me what I should do with my drawing. What I'm going to do here is I'm going to draw an air mass that is at 50% relative humidity. So here's my capacity, and I'm going to fill that box half full. That is meant to be half, although I think I've drawn it slightly more than half. So our air mass here is at 50% relative humidity. What that means is it has some capacity for water, and half of it, or 50% of it, is being filled. Now, who would like to field my first question, which you'll have to apply one of these two statements?
Excellent. Play with the lava lamp.
Anybody want to try to apply? Brianna, thank you.
The first one.
Okay. Now, if I warm this air mass up, what should I do with the size of this black box?
It should go like that.
It should go...
It will hold more water.
Yes, it can hold more water, so I should make the box bigger? Sure. Yeah. So I'm warming this air mass up. I'm going to, therefore, have to increase the size of the capacity that it can hold water. Boom.
Wow.
Now, who would like to field my next question? It's just a simple interpretation of that drawing.
What?
What, would you like to give it a shot, Oliver?
Okay.
Okay. When I increased the size of this box, what happened to the relative humidity of the air mass?
Down.
It went down. Yeah. You see how it was 50% before because it was filling half the capacity? But I pretty much increased the capacity by about 150%. And what that did was that made the relative humidity go down even though I didn't change the amount of water in the air mass. Okay. Next question for you.
No.
Okay. Who would like to answer my next question? It's going to be in a similar vein than these last two. Come on, somebody. Should I throw your name in the hat again?
Well, I get to play with the lava lamp.
No.
Then no.
Alright. Michaela, would you like willing to give this a shot? Okay. So knowing that cooler air masses can't hold as much water, if I cool this air mass off, what should I do to the size of this little black box?
Bring it down.
I should bring it down. I should make it smaller. Alright, so I'm making the size of the box smaller because I cooled the air mass off. Now, Caitlin, what happened to the relative humidity? It went up. See, now this same amount of water is filling a greater percentage of that box. So what you're doing here, what this is supposed to show you is that you can change the relative humidity of an air mass without changing the amount of water in it. It's had the same amount of water, but we've affected the relative humidity by increasing or decreasing the temperature, because that increases or decreases its capacity for water. So I'll write those things down now, and I'll give you a rule of thumb to remember how this works. So I'll say warming up an air mass drives relative humidity down. If the amount of water in the air stays about the same. Warming up an air mass drives relative humidity down if the amount of water in the air stays about the same, for exactly the reason I just illustrated. Warming up the air increases the size of the box here, the black box, and thus that blue box makes up a smaller percentage of the larger black one. The opposite of this is also true. Cooling down an air mass drives relative humidity up if the amount of water in the air stays about the same, because you're shrinking the size of the box and the water will fill a larger and larger percentage of it. Yes?
I don't think I'll
This.
but if the amount of water in the air stays.
Now all of this is based on this amount of blue in here. That's the size of that blue box not changing. If the size of that blue box changed also, then that would have an effect also. But if this blue box is just staying the same size, then the only effect on the relative humidity is the temperature of the air, because that's going to shrink and make the
So
black
the
box
whole
bigger.
box is the air mass, and so much on the box.
This one, that's symbolizing its capacity for water, how much water it can hold. And that's the actual water, like how much of its capacity can fill. Okay, do you want me to write who wants me to write the converse of that, or or is that implied, do you think?
It's fine.
Okay, speak now or forever hold your peace. Alright, the rule of thumb now is that basically the relative humidity does the opposite thing the temperature is doing. Relative humidity does the opposite thing the temperature is doing. If the temperature is going up, the relative humidity is going down. And if the temperature is going down, the relative humidity is going up. For, once again, the exact same reason I've just illustrated. Making temperature goes up, drives the size of this box up, and then the relative humidity is a smaller percentage. Let's imagine now we're going to shrink the size, we're going to cool the air mass off, cool that, temperature goes down, relative humidity goes up. To see why, we shrink the size of the box. Now, somebody look at this real quick and tell me what the relative humidity of this air mass is.
95%.
How about now?
Like
100. It's supposed to be 100. What I'm trying to do here is draw it so that the blue completely fills up the capacity. Now, we've cooled this air mass down enough that it's at 100% relative humidity. If we cool it off a little more, what's going to start to happen? Condensation is going to have to start to happen. So if you cool the air mass off past the point where it's reached 100% relative humidity, you're going to get either condensation or deposition. So, cooling an air mass past the point where it reaches 100% relative humidity will cause
Wait, what's RH?
relative humidity. Condensation or deposition. And if you look at any weather outlet, they'll actually tell you the temperature at which that will happen. We'll look in just a moment when people are done writing. If we look at our detail right now, it says the relative humidity is 37%. That's pretty low. Only 30%, 37% of this little black box is filled right now in the air mass sitting over Portland. Now, if we drive the temperature down, the relative humidity will go up, and up, and up. And on here it tells us the temperature at which the relative humidity will reach 100%. Where does it say that? It tells us right on there the temperature.
Dew point.
Yes, it's called the dew point. Now can you see why that's called the dew point?
Wait, so does that mean that there's condensation right now because the dew point is below relative humidity?
No, what that means is if you reduce, right now it's 56 degrees out, if we drove the temperature down, the relative humidity would go up. When the temperature hit 30 degrees, the relative humidity would be 100%, and then you would get dew. Actually, in this case, because the dew point is below freezing, you'd get frost. So tonight, if the temperature dropped down below or down to 30 or below, that means the relative humidity would be 100%. Water would start to have to condense out of the air, but because the surfaces around would be below freezing, you'd get frost instead. If the dew point is above 32, you'll get condensation, you'll get dew, and if the dew point is below 32, you'll get frost. You're about to ask something here?
I was going to ask what the temperature is to get dew.
Okay. Yeah. So basically, the dew point the dew point's not actually telling you when you're going to get dew. It's telling you when relative humidity is going to reach 100%. And usually that means dew, except when it's cold enough to not. Yeah. Okay. Should I write anything about the dew point there? Condensing air mass past the point where it reaches 100% relative. I'll also write like this is the dew point. The dew point is that point at which 100% relative humidity will happen. Okay,
No, let's
now I think knowing what we know about relative humidity and its correspondence to temperature, we can now answer just about all of these questions. Why can you see your breath when it's cold out? Well, because you're breathing out very warm, humid air, and what's happening to it when it gets into the air out here? Temperature of your breath goes down, so relative humidity goes up. When it hits 100%, it condenses it condenses on what? I don't know. It condenses on something, and we'll get more into that.
So that means that like when we're outside and it's cold, that means the relative humidity is like 5 if when we breathe.
The relative humidity of your breath is different from the relative humidity of the air. The relative humidity of the air in the winter is often very low, but when you breathe out, that breath that just came out of you has a lot of moisture in it. So its relative humidity is much higher. Okay, why does a bottle of glass or cold liquid sweat? It sweats because a humid air mass is getting cooled off by the glass until the point where it reaches 100% relative humidity. Same thing here. Why does a mug get frosty when it's taken out of the freezer? Because the humid air around it gets cooled off to the point where its relative humidity is 100%. Why does the mirror fog up when you're taking a shower? Actually, you know what fogs up even more than the mirror, although you may not have noticed it, is the toilet tank. There's a lot more condensation on the toilet tank than the mirror because the toilet tank is colder. It's got lots of water inside it. The mirror itself, the glass of the mirror, is not as warm as the air. It's colder than the air because the glass has a, what's that?
Higher specific heat.
Yes, the glass has a higher specific heat than the air.
Nice
The
job,
glass
Oliver.
stays a little
Thank
cold.
you.
Yeah. Okay, a couple others. Why is there dew on the grass or frost in the grass in the morning? Well, why is there frost or dew in the morning and not like in the middle of the day? What's special? What's special?
Because it's so
happens
cold
at
at night.
Summer.
So cold at night.
Yeah.
Temperature goes down overnight, so relative humidity goes up. 100%. Condensation or deposition.
Bam.
Why do we get fog so frequently along the ocean? Nick, you want to expand upon your answer that you gave me earlier?
Well,
Tell me there's a warm, humid air mass over the land, and what happens to it?
it hits the cold relative humidity.
It hits the cold air coming in from over the ocean.
Yeah.
So the relative humidity of the land air goes
Up.
up. until it hits 100%, then we get fog.
So I was right.
You were right, absolutely. The only piece of your answer that was missing was just the piece about the temp getting driven down and then the relative humidity get driven up.
Well, because
That's
we
fine.
just learned about it, so
Right.
there's almost no way.
Precisely, that's what I said. This last bit, clouds, there's something similar going on between clouds, fog, and your breath that is different from what's going on when you get condensation or deposition onto surfaces. And it's because you can see the condensation in the air around you. And I'll tell you this,
Wait, so are clouds just condensation up high?
yes,
So then how come today there's not a cloud in the sky?
because the air up there is not at 100% relative humidity.
You're wrong.
It's colder, right?
It is colder up high, but I guess the air mass up there does not have enough water in it to reach 100%. Now, water can't just spontaneously condense out of the air onto nothingness. It has to have a surface, a cold surface, or it has to have a surface to condense onto, something like a mirror or the grass or your car. So that begs the question, how do we get clouds or fog, or why do we see our breath? Because there's condensation happening, it appears to be happening into thin air, but it's not. There's actually something there that the water is condensing onto. Question?
Well then, how does rain form in clouds? Or does rain come from clouds, or does it just come
Yes,
from
and
the
we're
sky?
about to get there. Question?
Doesn't it like condense onto the molecules in the air?
Nope. Well, I mean, there has to, yes, eventually it can condense into other water molecules, but they have to be something to start with. So, real quick,
It might be actually wired.
It actually is.
let me run you through the... What's that?
You can donate.
Well, I need that space. Let me run you through the quick explanation of how clouds form, and then we will do our cloud in a bottle demo, and then we'll be...
What are we using the
on to
lava
the next.
lamp for? Is that just because it's great?
Well, actually, it will help me demonstrate a little bit about what happens to warm, less dense objects right now.
Like
So-
rain, right?
Cloud formation. Cloud formation. So we'll start from the beginning, where we have a humid mass of air down at ground level. Humid mass of air down at ground level. Remind me where the heat source is in the troposphere.
The ground.
It's the ground. So, this humid mass of air down at ground level is going to get warmed up by the Earth. So, humid mass of air down at the ground level is warmed by the Earth.
Yes.
Now, someone real quick tell me how my lava lamp helps demonstrate that same thing.
Well, I actually have an answer to that one and a question, so can I answer it then ask the question?
Sure,
It's because the bottom, that big black part of the bottom of the lava lamp is like a heat source.
right? And so it's warming up the stuff,
It's like the troposphere.
the wax down there.
That's whack.
I think it's wax or something similar.
Can we break it open and try it?
No. Was that your question?
No, that wasn't my question.
What was your question?
So, is the ground warmed, like, is it just because of the core of the Earth, or is it because of the devils? And
The sun warms it up.
Did you honestly just say devils?
The sun warms up the Earth, and the Earth radiates that heat out. This might be a little slightly more detailed explanation than you wanted, but light from the sun comes on many different wavelengths, all the way from infrared up to ultraviolet, and the air is not good at absorbing those different wavelengths, but the Earth does a better job at absorbing the different wavelengths. When the Earth radiates the heat back out, it's in a form called infrared radiation, and the air is good at absorbing infrared radiation.
So the ground absorbs the ones that the air doesn't absorb.
Yep, and then it sort of radiates it back out on a wavelength that is very easy for the air to absorb. So the heat from the Earth is much easier for the air to absorb than the heat from the sun because it's on a wavelength that's easier for the air molecules to absorb. Okay, so humid mass of air down at ground level is warmed by the Earth. Tell me what you see happening to the things that get warmed by the
It
Earth.
goes up, and then the cool ones go down.
They
And it
rise.
does it again and again and again.
Let's continue on. And actually, my shades show the same sort of deal. They say air gets warm, molecules spread out, becomes less dense and rises.
that shows some
Hey,
interest.
don't call me.
Don't
So-
call me stupid,
What this
AJ. That was
means.
rude.
Air mass.
Well, that pressure was at least. Nobody teaches
AJ called Nick stupid.
Mr. Green called me an idiot.
Like,
AJ's gonna beat Nick
you
up.
should do it.
That's all. Let's deal with it.
Okay, so air mass becomes less dense and rises. Now, tell me what happens to the temperature as you go up to the troposphere.
Lower.
It gets colder. So that air mass is going to cool off. As the air mass gets cooler, its relative humidity goes,
Up. Down.
Up.
Yeah, up.
they go this different directions. So air mass cools and rises.
That just sounds like Chewbacca.
And relative humidity goes up.
That's what it sounds like.
Yeah.
Do it again.
I'll do it a little.
Okay. The air mass cools and rises, relative humidity goes up. When the relative humidity of that rising, cooling air mass reaches 100%, what's going to happen?
Condensation.
Condensation. But it's going to be way up there in the air, and there's not going to be anything that we can see that it's going to be able to condense onto. It can't condense
And then
on
it
nothing.
condenses into clouds and turns to water into clouds and comes out as
Well,
rain.
you've missed one step, and I'll explain what it is. So, when relative humidity reaches 100%,
Well, let him finish writing first.
when relative humidity reaches 100%, condensation happens, and I'm going to expand upon that a little bit. Condensation can't happen into thin air. There has to be something for the water to condense onto. Fortunately, our atmosphere is full of small particles of dust and smoke, and the water can condense onto those. They're called condensation nuclei. A nucleus is the center of something. They're called condensation nuclei because each of those becomes the center of a new raindrop. Okay, so when relative humidity reaches 100%, condensation
That's
happens.
So cool. So inside, you're implying that inside of each raindrop there's a small particle of matter.
Probably a lot,
That is-
because the raindrops won't fall until enough of them collide for them to get big and fat. So when relative humidity reaches 100%, condensation happens onto small particles of dust and smoke that are called condensation
So when
nuclei.
they get up, like then does that end up in the clouds? Is that the stuff?
A big collection of these is called a cloud.
And then that's why it rains when a lot of those come together.
Yeah, they have to collide. When they first form, they're tiny, 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 tiny. If you ever walked out in the fog, you'll notice that the fog is not all falling down towards the ground. It's just sort of staying where it is because it's the mass of those individual tiny little water molecules is simply it's small enough to be held up by the air. When enough tiny droplets collide, they become heavy enough to fall
On this subject, then what is
as rain.
thunder?
I think you have enough information now to understand what's going to go on when I make the cloud in the bottle. So I'm going to do that now. First thing I need is some warm water. And fortunately, I've got a bunch of it right here. It's hot, but it's not hot enough that I can't stick my finger in it for an extended period of time. It's fine.
Boom, your finger comes out red.
No, it's not. It's probably like 120 degrees or something. It's not that hot. Okay, I need some of it in my bottle here. We'll put, I don't know.
It's good shower temperature.
That'll be enough. Now, the first thing to know is that, well, when you get to chemistry class, you'll learn more about gas laws and how temperature and pressure are related to each other.
Do you
Suffice
teach
to know
chemistry?
this. When I squeeze the bottle, what's going to happen is I'm going to give enough energy. It's sort of like fanning the water. Squeezing the bottle is going to give some of these molecules enough energy to evaporate into the air. Then when I release the pressure on the bottle, those molecules are going to condense again, but they're going to condense onto the sides of the bottle or on the water that's already there. So you're not going to observe anything really happening when I squeeze and let go of the bottle. Now what I can do, however, is I can put some condensation nuclei in here. And then when I squeeze the bottle and release it, a lot of that water will condense onto the condensation nuclei and you'll see a cloud in the bottle. The way I'm going to get them in there is basically I'm going to burn a small piece of paper towel and get some smoke inside the bottle. And then I'll be able to
I
make
want
a
to watch you
cloud.
burn it.
Well, you're going to see it in just a moment.
Let's see if it's burning.
Alright, so
That one.
What's the fire?
where's all the drug references today?
I don't know. I can't say it's that loud. Flame.
You're setting it on fire.
Amazing.
Okay, smoke in the bottle. Should be enough.
That actually looks really cool.
That's actually pretty neat.
Oh wait though, it gets better. All right.
So you're saying I could do this at my house if I
Yeah, that's all there is to it. All you need is a
I don't
bottle
think
and
you should be testing.
some hot water and smoke. So I'm going to squeeze the bottle, and then when I release the pressure on the bottle, you should see a cloud form in the bottle. You ready?
This is cool.
Here we go. No cloud. Cloud.
Wow.
Oh.
No cloud. Cloud. All that's happening there is I'm evaporating molecules, and then when I release the pressure, some of them are condensing onto the little
When
bits
you
of...
first put the smoke in there,